So I just wanted to, before, today is about networks. Just to close the topic, I'm going to make one exercise here in class, and actually I hope you kind of follow if those of you that want to follow. If not, you have the video for later. But I want to. But I want to just give a comment. I think that has confused quite a lot of people in the exercise. Actually, where is the chart? Okay, that chart that I told you that you have to make a plot like a Statoil is showing. Okay, so you get that plot, and I told you that I want you to reproduce the plot that Statoil is doing. Okay, and the plot that Statoil is doing, it's I think it's you have to correct me. It's here you have, I think it's TS, right? See, peak period, and then you have significant wave height, yeah, and you have a bunch of points. And then I told you you have to also plot the 100-year wave line, yeah, between the interval between 5 and 20, I think 25, 20, okay. So that you know already how to make. I think that was relatively clear. What you were asking me these days is how to put all of these points, and basically all of those points are the points that are in this diagram. Okay. So one way to plot it, there are many different ways, but one way to plot it, it's for example this point here. Okay. You can choose to plot it with that point there will have coordinates. Okay, let's make more space. Okay, that point will have coordinates if with t is x and y is h, so it will be the middle of the interval, exactly between 0 and 3, 1.5, and then with coordinate y 0.5. Okay. And you plot, and that will give you 1 point. Okay, the point will be, yeah, in this case, for example, someplace here and here. Yeah, there is no point. In reality, you have 16 points. But if you plot 16 exactly with the same coordinates, x and y, each one of them is going to fall on top of each other. So there is not really the effort. It's not worth the effort to spend all the time repeating these 16 times. Okay, and you do the same here and here and here and here and here. Okay, and that's how you generate all of. For example, that point here, it will be 17.5, and the y will be 15.5. Yep, and that should give you all the black region that Statoil has in the plot. Have you obtained similar? Those of you have done it. Have you obtained similar to what Statoil shows? Yep. Okay, not complicated. It takes some time if you're going to do it manually. If you want to use your VBA powers, you can use a VBA script, like a superpower, okay? And then you say you make a for I equal from here to here. Then you put another for j equal from here to here. And then you say take each element and make a pair, okay? Make a pair of points. You can also do that. We haven't discussed it here. I will see if we have time. But if not, you can do it manually. Okay? But I encourage you, for all of these repetitive tasks that you can detect a pattern, I suggest to kind of explore doing it with VBA scripts. Is there any other question that that you feel like you want to ask about the exercise? No? Yes?
On that question, when we are using trapezoidal, for the first time it
Which problem are you talking now? Problem 4, okay?
Yeah, when
Problem 4, don't use trapezoidal rule, okay? There the step is every month. If you use trapezoidal, okay, let's make an example. You have NP, PR, and then you have the Q that of the field, right? And that's time, okay? Times 0, 1, 2, etc. If you use trapezoidal to calculate NP, or actually delta NP, right? You will need the rate of that particular, right? And for the rate, you need the reservoir pressure, and the reservoir pressure also depends on the NP, okay? So this one is a function of this one, and this one is a function of this one, and this one is a function of this one. So you have kind of a circular reference. In that case, and probably you got that message in Excel, okay? So in that case, if you want to do it properly, you have to apply the solver, okay? And you want to assume a rate, and then verify if you can produce that rate. If not, repeat, and repeat, and repeat, okay? What I suggest, I'm not sure, maybe it was confusing in the exercise, this step is every month, okay? It's 1 month. So it's small enough that you really, it's okay to make a rectangular approximation of the curve, okay? You don't have to do trapezoidal just to avoid this uncomfortable process of iterating, okay? You can do it, but it will give you, due to the length of the step, it will give you or more or less the same result. Yep. Okay, so don't consider that, don't use trapezoidal for problem 4. Use, that's called rectangular integration instead of trapezoidal to avoid iterating or converging in every time step. That's why I told you to use just month, okay? Just use rectangular integration, that is for calculating delta NP, okay? That's why I told you do it every month. Okay? And that's a solution many times. Many times this convergence process, it's a pain. So many even commercial software, they tell you just use a very small time step, no matter. It will give you more running time, but you avoid the to put a solver in every step. Yep. Yes. More questions?
Isn't it the other way? You find NP and you can calculate the QL from that?
You can do it many ways. You can assume PR, that will be less than that. You calculate the rate, then you calculate NP, okay? And then you verify that that NP in the table gives you the same PR. You can close your equation with any, but for example, let's say
Could
I
you
assume PR, okay? Reservoir pressure, you obtain this QO max from the Vogel equation, then you obtain the rate, okay? How much I'm going to produce. Yes, QO from the field, okay? Now with QO from the field, you calculate NP, yes? And then with NP, you go and interpolate on the table, and you obtain a PR red, okay? And then you verify, is PR assumed equal than PR red from the table? No, then I have to repeat again that process, okay? And you can do it with NP, you can do it with rate, you can do it almost with any, okay? Here you could assume NP or you could assume rate, okay? But I prefer, if you're going to do it like that, I prefer that you assume reservoir pressure.
Why do you need integration? You have NP. What are you supposed to integrate if you have NP?
If you assume NP,
No, if you can assume NP 0 the first month or in month
Well,
0.
Let's maybe okay, let's say you have time, okay, NP, PR, Q, how much you're going to produce, and here you have the time, okay? That one you have, okay? You know how much you're producing, etc. You go to the next time. And when you go to the next time, you're assuming that you are going to produce that constantly,
Yes.
right?
Yes.
From time 0 to time 1. Yes? That's how you obtain the NP. Yeah. But really, in reality, if they are in plateau, it doesn't matter, okay? If the rate remains constant, it doesn't matter. Assuming constant, it will be the right NP to estimate NP. But if the rate changes, for example, from that step to the other, the stage decline, making a constant rate approximation, you are over predicting by this small part that is here. Okay, when you're approximating the NP, right? So you could say just this is equal to the previous times this t minus this t times the number of days in a month, okay? But by doing that, you are approximating, assuming that it remains constant since time 0 when you go to time 1, okay? And I'm saying if the step is very big, if this is 1 year, for example, that's a very bad approximation, because what you're missing in this small space is quite a lot of oil. But if this step is relatively small, if it's 1 month, then really to make it constant, you're not going to lose much in every step. Okay? Maybe we can discuss it when you have but just the bottom line is, if you on your exercise don't use the trapezoidal rule, just use the production from the previous step and the difference in time between the current and the previous for your exercise. Now if you want to do it, maybe we can, after you deliver the exercise, we can have a discussion and I can show you how to do it with the trapezoidal rule, okay, if you want to converge in every step. Yep. Was that the question, or was something else? Yeah, was that the question? We can maybe take it later after class if you want. Okay. Yes, now let's go. What happened to networks? Here. Okay, so let's to kind of try to settle the discussion on networks that we had last class. Okay, we had a discussion on how we solve when we have multiple networks, and I told you actually you have a system of equations that you have to solve, and you can do it that with any numerical method that is feasible. Usually we use Newton-Raphson. It's very efficient and it's very effective for these kind of problems. Yeah. So I'm going to talk now in class about the exercise 2, problem 2 in your exercise set number 3. Okay, just to use that as an example. And we have is Gullfaks South, and Gullfaks South has 2 templates. One of them has 4 wells, template L, and another one has 3 wells. They are commingled into a manifold in the template, and then there is a flow line that commingles the production to that template, and then you have one line that goes all the way to Gullfaks C. Yeah. In this case, we are going to assume that all the wells in a template, they are identical, just to simplify. Okay. But the two templates, they are different. The wells in each template, they might be different. Okay? So it looks something like that. You have 4 wells, template L, all of them are identical, so I can represent them by only 1. And when I want to compute the production of that template, I just multiply the rate of one well times 4. And then template M has 3 that they are different from those on this side, but when I want to compute the total production, it's enough that I just take the production of 1, multiply times 3, and that will give me how much is flowing to the tow head. And then I have a pipeline 14 kilometers, I think that's what it says here, 15, that goes all the way to Gullfaks. So it says that the field has been produced since 1999. Initially, you were producing oil. They were completed in the oil layer. But then at some point, the GOR was just so high that they decided to change them to gas wells. And what they have done, they have plugged the well in the lower formation, and then they sidetrack and they perforate, they drill into the gas layer. Okay, they have been recompleted in 2009, and they want to produce initially 10 million, but now it has already reached the decline. Yep. So your first task is to say, calculate how much naturally, okay, if I leave all my chokes open, how much I'm producing. And if you think, so if let's take, it's exactly similar to the 2 well exercise that we have done the other day. Or that we haven't done, but that we discussed the other day. So you have the equilibrium point. I have only one, the tow head. Yeah. So I'm going to say I'm going to go co-current from the reservoir all the way to the junction, and for that I'm going to need the IPR equation, the tubing equation, and the flow line equation, right? From seen P junction, seen from well 1. Then I will come seen from well 2, P junction, and then seen from the separator. Okay, and all of them have to be the same. Yeah, and we're going to do it in Excel, and it's a bit, so that's the principle. If you are a mathematician, I give you the equations, you can solve it very easily. But in Excel, it's kind of not so easy to set it up, so that's why I help you with the layout. Okay, so let's see, what do we have? I provide separator pressure. Okay, I say how many wells you have in each template, what is the reservoir pressure, the C and the N, and you see, if we continue further, the Q of the well, of each one of the wells, we have the tubing, then we have the wellhead. Okay, that gives you an idea that we are moving co-current from left to right, in this table. Then we reach the wellhead pressure, and at the wellhead pressure, I have to change from the rate of one well to the rate of the template. So actually I have to multiply the rate of each well times the number of wells in the template to move all the way to the tow head, and there I stop my my co-current. Okay, now my counter current is just one step, that is, I just move from the separator all the way to the tow head. Okay, yep. So let's okay, so let's first do that. Okay, we'll do it. So what I'm going to assume is going to be flowing, instead of rate, I will assume pressure. Okay, remember, with rate I have the problem that if I put it too high, then it becomes a square root of a negative number, if you remember that problem. So that's why I prefer, like opposite to what we did in the previous exercise, to assume a bottom hole pressure. So bottom hole pressure, I'm going to put a value very similar to reservoir pressure to start with. Okay, so let's put here, for example, 140 bar, and for example 90 bar, very close. Now I move from the reservoir to the bottom hole. So for that I have to use the IPR equation. And which IPR equation should I use? User defined IPR, the one that gives me the rate, right? And now I say, okay, use that C back pressure coefficient of one well. Now I'm moving in one well. Okay, I'm analyzing one well. N is here. You have to do quality control, reservoir pressure, and bottom hole pressure. Okay, gives me a relatively big rate, 3.3, and drag it down, 3.4. Yeah, I moved from the reservoir for each template all the way to the bottom hole. Okay, now I'm going to move to the wellhead. I still have to use the rate of one well. Okay, and which equation should I use here to get the wellhead pressure? But tubing we had two, right? So which one? P P2. Why? Because we make our system, right? The fluid is going on that direction. Here we have PWF, PWH. Which one is 1? Which one is 2? 1 here, 2 here. So we need P2 if we have P1. Okay, so let's say tubing P2. Okay, what do we need for tubing P2? We need CT, we need S, we need pressure, inlet pressure, which is that pressure, and we need the rate. Okay, we all the time have to check that it makes sense, the pressures that we're getting. Okay, this pressure is higher than that pressure, and that pressure is higher than that pressure. Okay, just to quality control my results. Okay, the same here. Now I have to move. Now is the crucial step. I have to move from this point, from the wellhead, to the junction, right? But there I have one flow line, and I have actually 2 more wells or 3 more wells in the case of template L that are very close to it. So I should use, I assume that all the wells, they have the same wellhead pressure, okay, because they are so close to each other. If you see all the wells, okay, they're very close to each other, so all of them have the same wellhead pressure. But now when I move all the way to the junction, I have to use the Q of the well times the number of wells in the template. That clear? Yeah, and I still move co-current. So for that I have to use, first I have to calculate the Q. That will be the rate of the template times the number of wells in the template. And let's make some quality control. We said that the rate the field was producing at how much was it? Plateau rate 10 million, okay? And we are getting like 2 million total from these two. Let's make the sum. Which it's, you know, it's maybe it's expected that this is less than 10 million, okay? It's 2 million. Maybe it sounds a bit low, but let's see what happens. Now I move to the towel head, and here I have to use which equation? It's line, right? We call it line, but P1, no? Yes? What are we want to calculate? We're moving from P2. We are moving from wellhead. No. Now we are just moving from. We haven't calculated the pressure at the towel head. Okay? We are moving from here to here. Yeah? So we need P2. Line P2. And I need flow line coefficient. I need the pressure at the inlet of the pipe. That is this one, right? And I need the rate. And here I have to be very careful. I have to use the rate that is going through the line, which is the rate of the template. Okay? And you see they are different. And that's an imbalance in the network, and I cannot have such an imbalance. Okay, I have to increase one of the rates. Okay. Let's see, how can we make them equal? For example, how can I increase the pressure drop? Okay, let's say we can make it equal by, you know, it's almost like a class in economics, right? I can bring that guy down, okay? I can tax more this guy, and I can tax less this guy, right? So how, let's see, the only variable that I have for changing is the bottom hole pressure that I assumed, okay? So now let's see what happens if I assume, what should I get? For the pressure losses to be higher, I have to use what? The frictional losses should be higher, right? And for the frictional losses, are higher, then the rate should be higher. If the rate is to be higher, then the bottom hole pressure should be lower. Okay? So here, let's say, put, for example, 120, maybe. Okay? Now it's much better. The difference is in 20 bar. Okay? Now to help this guy should be producing less, a bit less. Okay? So to produce less, I have to increase bottom hole pressure. Okay? Close enough. I will let the solver to do my work. And now the only thing that was missing was to calculate the tau head pressure as seen from the separator, counter current. Okay, so for that I go again here, I say line, and in this one it will be P1. Okay, I'm moving, I have P2, I want to calculate P1. And C flow line pressure 2, it will be that pressure here, okay, and the rate will be the rate of the field, the full rate of the field, right? 62. So you see they are not the same. Now I want all of them to be the same, and this is where the trick comes. So how can I make all of them the same? Remember that the solver, when we call the solver, it needs only one cell. Okay, we cannot say this cell equal to this cell equal to this cell. Okay, we need one objective. So I'm going to show you just one way to put all the cells in the same, to put all of these in the same cell. Okay, it's one way. There are many ways to do it. But first we are going to calculate an average pressure at the junction. Okay. Then we are going to say the deviation of each one of the junction pressures calculated from well L, from well M, and from the separator with this average pressure. So I'm going to say this number minus the average. I block the average and then squared, and I drag it down. Okay, and then I make the sum of all of these errors, right? Now, when all the pressures are the same, they should give the same average. They should give an average, right? That is just equal to the pressures, right? If the average, if you have 3 junction from well 1 plus P junction from well 2 plus P junction from separator, okay, divided by 2, that's equal to P average, right? If all of them are the same, the deviations between should be going to 0, right? Okay, so it's a bit tricky way to do it, but that's how I created one cell, one error, that I will call this error, that I want to minimize. Okay, let me just put it like that. And if you want, I want to put an equal, okay, but I don't want to think that it's a function, so I'm going to use, okay, just that apostrophe. The apostrophe makes it a comment, okay, and it doesn't consider it a function. Now I can use my solver, and I say, solver, please change. I want this number to a minimum, okay, to 0, by changing what? What am I assuming? Bottom hole pressure, okay, these two cells. And should I put any constraints? Well, let's first try to solve what happens and see. Okay, found a solution, all the pressures are the same, the average is the same, and it tells you that that well has 100 bar, 80 bar, and the total production is 8.5 million. Okay, and you were producing 10, so you say, okay, it has depleted, but not really, not that much. That clear? Yeah? Think you can reproduce it with a more complicated example? Okay, by the way, that exercise was given in an exam from last year. Not sure if it was a receipting examination or the Okay, now let's go to, now let's see what happens. This is kind of a variation of this exercise. It tells me the field manager, okay, or the reservoir engineer wants to produce let's say he wants to produce where is the rate of the well 1? Yeah, 1.5 e to the 6 from each well in template L, and 5 e to the 5 from each well in template M. Okay, is that possible? Okay, reservoir engineer said, by any reason, maybe we're producing more from some other wells, maybe some reason, he says, please put exactly one the wells from L to produce 1.5 million and the wells from M to produce 500,000. Okay, and you smile in that moment. You are an engineer in the company, and you smile because I told you, right, that when you fix the rate is the happiest moment in your life. When you want to do equilibrium, then you need the solver, you need to pose your problem, it takes time. But when you have fixed rate, it's just verification. Okay, you go substitute the rates and see what are you going to check. What is the element that you can change in all of this system? In all this system. Didn't put the plot here. The choke, okay? That's what I can adjust. All the rest is fixed. I have no valves or anything any other place in the system. So the only thing that I can change is the choke. But then, if I'm given the rates, okay, I have to calculate the choke will be my equilibrium point, pressure above it, okay, upstream that, pressure downstream that, and it should be positive. Yeah. So how do we do it in our sheet? Okay. Yeah. Let's first erase everything that I have done so far. Okay. Error, etc. Okay. So now let's say I will start by assuming the rate, because the rate that I have, the reservoir engineer gave me 1.5 e to the 6, right? And 5 e to the 5, right? And these are not, let's change the color, so these are not calculated variables, but they are given variables. Now, bottom hole pressure, I can calculate, right, with the IPR equation. IPR, PWF, and I say I want CR and reservoir pressure and rate. Okay, and this should be in blue because that's values that I calculate. Now, what happens if at any point you obtain a value error here? What does it mean? Well, it means that you have this square root, right, of a negative number. And if you have that number, that means that that rate is physically impossible, that you need a pressure actually that is negative. And that's not physically possible. So if you already get here a value error, you can just go and to the reservoir engineer and say, no, you cannot produce that rate. You don't have enough. Your IPR doesn't let you produce that rate. Okay. Then I progress all the way to the wellhead. Okay. I say, so here I have to use which equation? Tubing P2. Okay. And I say CT S P1 will be bottom hole pressure, flowing bottom hole pressure, and the rate of the well. and I still have some kind of yep. Okay, now let's now that's my equilibrium point, right? The choke is my equilibrium point. So I have to stop there my co-current calculations, and now I have to start my counter-current calculations, right? To move from the separator to the tow head, and from the tow head all the way to the wells. Okay, so let's start doing that. And the Q of the field. So these rates I can already fix them, right? Because I'm fixing the rates. That rate times the number of wells in the template. That rate times number of wells in the template. Okay, and the Q of the field. And then I will to calculate the tow head. For that I use line P1, right? Because I have the pressure at the separator at the end of the line, and I want to find the pressure at the tow head. And here I need the flow line coefficient, the separator pressure, and the rate. Okay, 65. And then I move from the tow head, okay, I move from here all the way to the templates. And how I'm going to call that pressure? Actually, I don't have here a column to make it. Okay, I have pressure here at the tow head. So I should make another column called pressure where? At the template, maybe we can call it pressure at the template bar. And this pressure will be using that pressure, right? I go counter current and using the rate of each template. So here I should use which equation? Line P1, okay, with the flow line coefficient, with the pressure, this pressure, and I can block it, okay, because that's going to be the same for both, at the tow head, and the rate of the template that I just calculate here. And I can drag it down, I guess. Yeah, that looks correct. Okay. Okay, so what's the first thing that I check? I calculate delta P of the choke, right? Okay, bar. And I say it's going to be pressure upstream the choke minus the pressure downstream the choke. 12 bar pressure drop and 2.8 bar pressure drop. Okay, the rates are feasible. I'm happy. I can say to my reservoir engineer, yes, you can go and sleep tranquilo, you'll go and sleep calm, we will be able to produce the rates that you want. Okay? And you can also see exactly what I told you. If you want some other rates, for example 1e to the 6, that will also be feasible. Okay, you need a delta P of 34. Interesting, I changed the rate on one well, okay, on template L. What happened? Did this remain the same? Can I leave the choke in the same position? The choke of the other template. What did you see just now? Let's click undo. Okay, that was the initial case, right? 12.8 and 2.8. What happens when I say my reservoir engineer comes again and say I want to produce exactly 1 million? You're going to say, oh, I just go and change the choke on template L, right? That's it. I don't see, but you see, I also, if I want to keep the same 500,000 rate from template M, I also have to change the choke in template M. And that's exactly the essence of the network. Any change I make in the network is going to affect, up to a certain degree, all the other elements in the network. Okay, so when I think in a network, I have to be careful and not think, okay, I will treat that individual well, because it's going to have enormous effect on the rest. Yeah. Now I could try to say what happens if I want to produce 1.8 e to the 6, for example. minus 4.9. Now that's a warning. That means that if you remember the drawing that we did last class with the feasible and unfeasible area, okay, we are using a combination of rates that are out here that I cannot produce just by simply choking. Okay, would we take a break? 15 minutes? Okay. So we have now one exercise. The deadline is next week on the 6th, right? On Monday. Then you already have another exercise published that you asked me to put it in advance. So that goes from the 7th all the way to the 21st. So you have, let's see, second exercise that the deadline is the 6th of March. Okay. Then the third exercise, the deadline is on the 21st of March, sorry, not May. Then the fourth exercise will be will probably be by the just before Easter. Okay, will be just so you can enjoy your Easter in peace, I hope. Okay, so it's 9/4, and then the fifth will probably be just by the end of the semester deadline. Okay, so this is tentative plan. Okay, don't take it like these words from the Bible. It's just words from me. Okay, but is the tentative date, and the last one will be probably by the 5th of May. Okay, just be 1 week before the exam deadline. Okay, that's tentative. I will put it here in tentative plan. Please. Tentative. Okay, don't come later and say you said exactly on the 9. So I'm going to put here plus minus 30 days. So I'm using a characterizing the value with a correct uncertainty. So I will be safe. Maybe let's put 90 days. Okay. Okay. 6th, 21st. Let's see if that sounds correct. So you get, I think, 2 weeks for each. See, 2 weeks, and actually that you get a bit more than 2 weeks, 2 weeks and something. Okay, so this has to be more powerful. That has to be kind of a more powerful exercise. Set. Okay. Okay, now let's continue with the exercise. So now let's say if now we place, okay, we know that we cannot deliver 10, but if now we place a subsea compressor at the tow head, and we will have maybe, in 2 weeks or 1 week, we will have work a bit on design of subsea boosting in more detail. Okay, but now we are going to look what happens if we install a compressor. I think I have to close that, otherwise they chase you. Okay. How much if we want to deliver a rate of 9? Okay, 9 million. Okay, the natural flow, if you remember, was 8.5, and now let's say I want to produce exactly 9. Okay. First, they ask you, will that be possible? Okay, and if it's possible, then tell me how will be the pressure increase that I need from the compressor. Yeah. So for that, in the same Excel sheet, I have prepared for you task 2, a way to help you to organize information. So what do you suggest how to make that part, task 2, the compressor? No sounds, no suggestions, no. Okay, we have a given rate, right? Okay, and the rate, when I told you, when you're given a rate, you're happy because you can just calculate delta P, right? But in this case, you're not too happy. You have just half a smile. Why is that? Well, first, that the rate that you have is only on this line, but you don't know anything about these two lines. You don't know how much is circulating through each template, right? So that means I still have to make some kind of solving process to find what do I need to find. Let's say here I have the rate, right? I want to produce exactly 9 million. I have that pressure, and I can calculate the pressure downstream the compressor first, okay? Great. Now, I know that the sum of these two, they have to be exactly 9. Yes? Okay? But I don't know that pressure. So one option will be to make the first, they have to have a common pressure, okay? And the sum of the rates has to be equal to 9. Yeah? So what I suggest, and you will already know how to make the pressure equal, right? We use this average trick. We take the average of these two, say the difference between them has to be equal to 0. And then the solver also, I can add constraints, right? So I can say also, solver, please drive those rates to 9, okay? Anybody has another more clever idea? Sometimes we get some mathematicians that they see it right away and they find a more intelligent way to do things. No mathematicians here today? No? Eric, you are a mathematician? Yeah? No? Everybody's waiting for you, so. Okay, so let's do it the engineering way, Milan's way. Not the most effective, but let's see. Yeah, so I have the sheet, if you see, looks exactly the same, right? But now I say the rate that I want, okay, and the rate that I calculate, and these two, they have to be the same. Okay, and I have another error here for the rate. So let's do it step by step. Let's first do what we know is I have that pressure, I have that rate, and I move counter current to calculate the pressure downstream the compressor. That I know, that's the easiest thing to make. So I say pressure at the tow head will be, well, actually pressure downstream the compressor. Okay, I have it here. That will be line P1. Okay. So now it's like repetition, okay? I hope that you get it inside your head when you wake up in the middle of the night. Line P2, line P1. You have to have that, reach that level of rate. Okay, 67. Fine, it's very similar to what we had before. 65, 67, so we are suspecting already that the delta P from the compressor might be very small. Okay, before, how much did we get? If you remember the results from before, 66. Okay, so really is really not much difference. I should have 1 bar or 2 bar difference maybe. So now how do I make for the other two, for the two wells? Okay, for the co-current part. Okay, let's make it exactly the same way. Okay, let's say assume a bottom hole pressure. I go up to the bottom hole, I go up to the wellhead, okay, and then I go all the way to the suction of the compressor. Okay, let's do it exactly the same way to keep things the same. So here I assume again 140, a value very close to the reservoir pressure, maybe 90. Okay, the rate I use IPR QG. C back pressure, coefficient, reservoir pressure, and PWF. Then I calculate which equation do I use here, tubing. P2, okay, Just checking. Nobody should be sleeping. P1 pressure at the bottom hole and the rate, the pressure of the temperature, the rate of the well. Okay, and the rate of the template is just the rate of the well times number of wells. And then I can calculate the sum, how much these two wells are going to be producing, right? And you see now there is a big deviation. I'm saying 2.3 and they should be producing 9. So here I can put an error, okay, that will be this number minus this number squared. Okay? Yeah? And I know I have to put that number to minimize it somehow in my solver. Yeah? Now I progress, I have reached the template. Okay, I have reached that point and I have to move one step forward, call current all the way to the suction of the compressor, the tow head. Here I say line P2, okay. C P1 is the pressure at the wellhead and the rate is the rate, be careful, the rate of the template. 75. And we can really, we could make, you know, just the difference of them, right, equal to 0. We have only two values, so we can say one minus the other, the square has to be equal to 0, right? And that should be equivalent to the average. Should we try that way? I didn't try that way, but we can try. That minus that squared. Okay. So now, what do I have to ask the solver to give me? What do I have to, what kind of solving thing, procedure I have to make in this sheet? Okay, what has to match? I have two variables that I assumed. Okay, those are the ones that I'm going to change. I'm going to change them such that that value will be 0, right? And such that that value will be also 0. Okay? So let's try it this way. Okay, let's see. Data solver, please. I'm going to say the main one is this one, the pressure difference. The pressure at the tow head has to be the same. I want to minimize it by changing these two bottom hole pressures. Okay, but now I say add a constraint. I say the constraint is that the value of pressure that you find here has to honor that the rate is exactly 9 million. Okay, that rate has to be equal to, that difference, sorry, has to be equal to 0. Okay? Ready? Set, go. Error, okay? Why? Let's, okay, what's the problem with solving, you know, all of these iterative solving procedures? Okay, if you get that error here, is there something that you did wrong on the setting up of the solver? No? Well, there are many things that can go wrong, okay? One thing is that, for example, what happens if the solver tries a value higher than reservoir pressure? Okay, that's possible, right? I haven't put any condition. I have put the condition, if you see here at the base, that make unrestricted, unconstrained variables non-negative. Okay, so all the values that is going to try here, they will be all the time positive. And that's fine, okay? Pressure has to be positive. But is anything prohibiting the solver to use here 150, for example? No, right? So that's one thing that you have to, if you make more conditions, you maybe will make your solving process more robust. Okay? And if you remember, if you just, maybe it's not exactly, for example, you have, okay, a function that is relatively steep, okay, and continues here, does something else. Okay, if you remember, from your kindergarten studies or something, when you try to evaluate, okay, for example, if you're in that particular place and if the function is very, very steep, depending on the conditions of the function, the next seed, okay, remember that you try to find it with the derivative at that particular point, Newton-Raphson, okay? Newton-Raphson. If you remember what I do, if I'm at this particular point, initial point, x1, and I want to find x2, I shoot with the derivative and I find the next point, okay? And if, depending on the function, if it's very steep, I might be even out of range. Here, if, for example, I have 140 bar, okay, and I shoot and I get 300 bar, it's going to be undefined, my model, okay? Here, actually, the function is indefined, doesn't exist, right? So these things, we have to, that might be many reasons why I have that error. So what I suggest is to use a nice initial seed that we know maybe something closer that will shoot and take us closer to the final solution. Do we have such an initial seed? Do you think? Why not to use from the natural equilibrium that we solved just now, right? Let's try that. What values did we have? If you can check on, well, maybe I can check on my notes. We had 99.6 and 80.4. 99.6 and 80.4. Okay, and is that really what we had? Yep, but why the rate now is higher? 8.4. Okay, yeah, it's the error which is high. Okay, so let's see again. Still the same problem. So maybe something wrong with this residual. Should we try the same way we were doing it before? Yep. Let's see. Average, then this value minus this value, block it, squared, and the sum. So let's see again if we did that correctly, that the actually is this value, right? That should be minimum. Then by changing those two and by making the rate, which is K10, equal to 0. Okay, even worse. So we should just retire and abandon the ship. Why now is giving 0? Is there something I'm not seeing? That one goes to 0 by changing these two and changing that. Oh, but you see that one is already 0. Okay, so we might be satisfying part of the problem, but not that condition. Okay, that should be 0. Suggestions? No?
Was the wellhead, the bottom hole pressure limited by the reservoir pressure? Like it couldn't exceed it?
Yeah, but I think here the case is that the error is already 0 to start with. So that's why I think let's make let's see if we look only at that system. Okay, let's decouple the system. What happened here? Okay, let's look now just at that system, okay, that have two wells, the flow line, okay, well, actually more wells, and here I have a common pressure, okay, pressure at the junction, right? If, let's say, imagine for a moment, if P junction was given, okay, let's say P junction is given, can I solve that system? Can I calculate how much is being produced by well 1 and well 2? Yes or no? Yes, right? No problem. Now I will solve it and I will get certain total rate, right? Now what I want to plot, for example, is if I change that P at the junction, okay, and then I plot the rate that I'm going to get, okay. Initially, if P junction is very small, the rate is going to be very big, okay. But now when I start increasing, it's going to decrease, 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 until I find an intersection point. Sorry, that's okay. No, sorry, just it's going to decrease, right? No zero. Just it's going to decrease. Yeah, all of you have shared that. Yes? If P junction is less, I should produce more. If P junction is higher, then I should produce less, right? What we are looking for is the pressure at which the rate is exactly 9e to the 6. Right? I want to find exactly this pressure at the junction. Yeah? Yes? Agree or not? So let's so what we can do in our solver, okay, we can say that I give certain pressure, okay, for example, given, okay, that's given P at the tau head, given, and that will be, for example, I will use 60. If 65 gave me 8.4, that means I have to use a lower pressure, right? So I should try with, for example, 62, okay? That's given, okay, so I change the color, that one will be given. And I say, again, the difference should be 0, right? Okay, so I say calculate, I use my solver, but now I don't include that condition, okay? I take it out of the picture, and I say solve, okay? And it found what rate? Oy, by coincidence, 9 million, okay? Yeah, at the first try, I was a bit lucky, I guess. Okay, but you see, if you, for example, we have tried, for example, 59, okay, or 58, well, not 558, 58, okay, you go here, solve, yeah, and you get a rate that is higher than 9, and you get exactly when it crosses between, when it's exactly 9, the intersection between them, and you know that the pressure that you need in the intersection is exactly 58, okay? For example, we try, what do we try initially? We tried 67, I think, the pressure. Okay, let's solve it. Okay, we obtain 8.41. Okay, so we start making our plot. I'm not sure what happens here. That okay, for our case, okay, P junction, and we have here the rate of the field. Okay, and we are solving for P junction equal to 60 what? 67 was it? And that gave me a rate of 8.41. That's in bar, and the rate is 8.41 e to the 6. Okay, that's in standard cubic meter per day. Okay. Then I try with another number, okay, that gave me something less than 9. 9 will be someplace here. 9e to the 6. Okay. Now I try with another point, which we said was, for example, 58. Okay. And we have 9.49. Okay, actually we got a value which is higher than 9. 58. So we have here 58 and we got 9.49 e to the 6. Okay. And we can continue, we can make, for example, a straight line between these two. Okay, that's, I think that's called it's not the bisection, no, it's how do you call this method? I forgot. That you make a straight line, you check the intersection. That's not bisection. That's bisection method, right? Yeah. Okay. So you find that point, and then you try again until you reach convergence, and you're going to reach, the solution was 62 bar, right? 62. 62, 9 and 9. Okay, that means that the delta P of the compressor, what my compressor has to provide is the pressure downstream the compressor minus the pressure upstream the compressor. That means 5 bar. How much my compressor has to provide. I advise to try to get it running with the solver. Okay, maybe you have to add a few tricks on the setting of the problem, but I advise try to play a bit with the solver to see how you can get it automatically without using this solution that I got here. Okay, I got it yesterday, but I'm not sure why I'm not getting it today. Okay, clear? Yeah. Okay, we have here it's a situation that is half fixed rate, half network, but we have to use, at the end we have to fall in network solving no matter what. Okay, now the next problem. Okay, in the exam you didn't have to deal with the solver because I gave you the curves, okay, the available and the required curves. So you had to do the same but using the curves, and with the curves you could find very easily the intersection. Okay, it says, in case, if now I install my compressor, okay, but the rate, if it exceeds 6.4 e to the 5 of template L, and it should be 6.4 e to the 6, I think. Yeah. 6.4 e to the 6, they might be wellbore collapse, okay, stability problems. When the pressure in the reservoir declines, then you have problems that maybe the sand phase might collapse, okay, due to the reduced pressure. So the reservoir engineer told you, please don't take the rate, don't put it higher than 6.4 for that particular pressure. Okay, so they told you, okay, one solution is to choke. I can choke here, okay, to reduce the flow from the template. Okay, can I still produce this 9 million? Okay, you see the problem? I still want to produce 9 from this line, but I don't want to produce more than 6.4 from here, from this template. I want to produce, yeah, but that's per well, sorry. So that's 6.4 per well. I know, it's the flow, so it should be e to the 6. That's an error. Okay, so how do we solve it? So the problem is, that's task 3. Okay, we have two systems, the same, then we have a compressor, and then we have the flow line. We know we want to produce 9 e to the 6 here, and this rate Q from L has to be less than 6.4 e to the 6. Okay, is that possible? Any ideas? No ideas? Well, what we can say is that we can do the same thing that we have been doing so far. Okay, we move from here, counter current, calculate the pressure at the discharge of the compressor, right? Yes. Then we move from reservoir pressure. I think, if this well was producing in the previous case, okay, was producing 7.2, okay, it's very likely that I can lower it to 6.4, okay, that I can just choke it and take it to 6.4. Okay, so I can fix the rate 6.4 in this line, and I will have a delta P of a choke that is unknown, okay, but that I have to so let's see. If I fix that number, right? The total production of the field. I fix that number, the total production of the template. Do I have this rate? Yes, right? Because that's just 2.6 e to the 6. Yes? Okay? So I have all the rates. I have the ideal situation that I want, right? Or not? Yes? Okay? So what will be the sequence? Calculate counter current, the pressure at the discharge of the compressor. Calculate co-current with that rate, the pressure in the junction. And calculate co-current, the pressure at the upstream of the valve. Okay? Okay? So let's start doing it. Okay? So that will be task 3. So first I assume the Q of the field that I want is 9 e to the 6. Okay, that's what I want. Okay, and I calculate now pressure downstream the compressor, that is line P1. Okay, rate, then I need is the pressure. The pressure is here, and then I have the rate of the field. Okay, 67.2 doesn't change, should be the same as for the other case. We are keeping the rate constant. Okay, now I move, these two rates are given. Okay, I say they are given value, so this one will be 6.4 e to the 6, and that one will be just the difference between this number and that number, right? And we can put it calculated. Yes. So now with that rate, I go co-current. Okay, both wells. I go IPR PWF, CR, N, and reservoir pressure, and the rate. The rate is here. And what happened here? That is not giving any result. Sorry, this is the Q of the template. Okay, so that Q should be here, and the Q of the well, it's actually that rate divided by the number of wells, right? Yeah, very important detail. Okay, and here I can put IPR PWF, CN PR, and the rate. Okay, and the other one. Then I move all the way to the wellhead. Okay, and this will be tubing P2, right? And tubing P2 is using CT SP1, that will be bottom hole pressure, and the rate, that is that rate. Okay. Now, you see I have two pressures, which no, but now here I'm at the wellhead. Okay. can I move now from the, so let's see my diagram. What, so now where I am, where am I? Okay, I have done, let's make it another drawing so it will be less messy. Okay, I have moved from here all the way to the P downstream the compressor. Okay, that should be fine. Okay, now I move from the formation all the way to the wellhead for well in template M, and from here to here for template L. Can I continue? That's the question. Can I continue from for these two wells all the way to the suction of the compressor? Yes or no?
Yes, yes.
Depends, okay? For well M, I have fully open choke, okay? I'm saying I'm not choking the wells from template M. So I can continue all the way to the suction of the compressor. But what happens with template L?
Just choke.
The solution that the engineer provided was to choke the templates of well L, okay? So here I have a bridge. I have a difference in pressure that I don't have, okay? That's what I have to calculate. So I will assume, just for now, let's continue on template M all the way to the suction of the compressor, okay? All the way to the tow head. So let's say only M, and now we need line P2, okay? We are co-current, and we want to calculate that the C of the flow line, P1, that will be the wellhead pressure and the rate of the template. Now, should the pressure, that's the real pressure, okay? Because that's the real rate. I have used now everything that they told me, okay? All the data that they told me. I have used, what's happening? 2.4, the reservoir pressure, open choke all the way here. So that should be the real suction of the compressor, okay? The real pressure at the suction of the compressor. Now I have the rate, okay, of flow line L, and I have the pressure downstream. Yeah, so I can calculate the pressure upstream, that will be the pressure at the downstream of the choke of wells in template L, right? And from there I can calculate the delta P of the choke. Do you see that? Yeah? Okay, so we move. So we have that P at the tow head, okay? I assume it's the same for template L, okay? Now I move backwards to the P of the template, and I need here one more column that will be P of the template. Okay, for the case of template L will be just wellhead pressure. Okay, I have no choke. This should be in this color. But for this case, it will be calculated using line P1, okay? Because I have the pressure at the tow head, at the suction of the compressor, and I want to calculate the pressure at the template. So that will be using flow line equation. Pressure 2 will be pressure at the tow head, and the rate will be the rate of the template, 41. The delta P of the choke is just the wellhead pressure minus the template pressure. Okay? That means it gave me a positive number. That means that it is actually possible to produce 9, is many constraints, okay? 9 million from the field. I have 6.4 million only from template L and 2.6 from template M. It is possible, okay? Now, what do I have to pay? Okay, now you say, okay, now it's completely different case. So what is the difference between that case and the previous case? What do I have to pay? What is the trick? Okay. So what I'm asking you, what is the trick? What do I have to give in return to operate in these conditions? There is one element that we haven't discussed now, that we calculated in the previous case. What is that? The compressor. Okay? The compressor here we said 5 bar. But here we haven't. How much do we have to compress actually? And you see, let's see, the discharge is 67 minus the suction is 41, 25 bar. Okay, now I know what do I have to pay. I have to compress much higher, I have to breach a much higher pressure difference such that I won't damage wells in template L. Okay? They look the same, but they are not the same, these two cases. Okay, I'm producing much less, and because I have to produce much less, the pressure at the suction has to be lower to produce more from this template. Okay, and because of that, the pressure has to give a higher pressure increase in the line. Yeah, that clear? More or less? Yeah. Anyhow, you will have to work with it, so you can have some time to refresh it and think about it, but just to give you kind of a start, and that you have many, it can become very, very complex. Simple equilibrium, relatively easy. When you fix the rate, relatively easy. When you start having some mixed systems, then it becomes a bit more challenging. Okay? But if you have fixed rates all the time, you can, if you think about it in a smart way, you can calculate what you need. Okay? Yes, any question before we close? No? Okay, so see you next, enjoy the weekend. See you next Tuesday.